Hello, everyone. So today we're going to continue our conversation on colligative properties by talking about osmotic pressure and a little bit about solubility. So it turns out that we can actually treat both of these properties, again, very similarly to how we dealt with freezing point depression and boiling point elevation by looking at the changes of chemical potential of a solvent. So osmotic pressure essentially relies on the principle that if I add a solute to a solvent, it's going to essentially lower the chemical potential of the solvent of interest. And one of the ways we can essentially take advantage of this is that when you place essentially a pure solvent next to a um, solution, you're going to see a certain flow of the solvent to essentially the system that has a higher concentration of impurity. So essentially towards the mixture. Well, it turns out that you can actually slow down this process by applying a pressure, pi, which we're going to call the osmotic pressure. So this is essentially the amount of pressure that it takes to essentially impede the flow of solvent. There's actually several ways you can take advantage of this property. One is that you can actually use this as a form or a method of doing work, where you can essentially allow the solvent to move into the new system and expand. Alternatively, another approach is you can apply more pressure than the given osmotic pressure to make our solvent move to the pure solvent system in a method that's called reverse osmosis. You may be familiar with this idea through reverse osmosis filters, where you put a filter on one side, say contaminated water, and then you essentially apply pressure to essentially remove any sort of solutes. However, in order to try and model this system, we're going to try and figure out exactly what the osmotic pressure is for essentially two systems to come to equilibrium. So in order to determine this, what we're going to do is set the chemical potentials of my pure solvent equal to the chemical potential of pretty much my contaminated system. So the biggest differences in between these two systems is that we're going to have to apply an extra pressure to my mixture, as well as it will have a composition dependence, as it's going to have a certain mole fraction of solute present. So what we can do is, again, set these chemical potentials equal to each other, where I have the chemical potential of my pure solvent, and that's going to be equal to the chemical potential of my solvent plus essentially this composition factor, which is going to lower the chemical potential by stabilizing the system due to entropy. And then I'm going to correct it by pretty much this work term of applying extra work to the system, or essentially destabilizing it by adding in an extra energy. So in order to do this, we're going to have a classic integral of VDP sort of work. Now, what we're going to do is we're going to integrate this system to figure out how much extra energy is provided by integrating from essentially my the normal pressure that's experienced by both sides. Typically, this is going to be 1 bar. And then we're going to essentially do an ending pressure, which is the starting reference pressure, plus essentially my osmotic pressure. Now, when we do this, what we're going to end up with is a rather simple integral. I'm going to have the molar volume of my system times the osmotic pressure, as the two reference pressures essentially cancel out as VMP minus VMP. So when we do this, what we have is the chemical potential of my pure solvent is going to be equal to the chemical potential of my pure solvent plus essentially the correction factor for composition, plus the extra energy provided by applying osmotic pressure to the system. Now, you may notice that certain terms are going to cancel, most notably the chemical potential of the pure solvent. Then what I can do is essentially move this composition term over to the other side. And what I'll get is the molar volume times the osmotic pressure is going to be equal to negative RT of the natural log of the mole fraction of the solvent. But again, like with our boiling point elevations, we're going to be less interested in the mole fraction of the solvent and more interested in the mole fraction of the solute. And we're essentially going to do a similar strategy by converting to natural log of 1 minus the mole fraction, and then essentially expanding out the natural log to get a term of just the mole fraction of the solute. So now we have a rather simplified set of equations where I'm going to have the molar volume times the osmotic pressure equals RT times the mole fraction of the solute of interest. So essentially how contaminated the system is. Now what we can do is actually rearrange the system a little bit more, as I'm going to say be solving for the osmotic pressure of the system. When I do this, I'm going to have RT times the mole fraction of the solute over the molar volume. Now, you may notice that we're going to start seeing some things that might be able to cancel out. Most notably, the molar volume is the same as the volume divided by the total number of moles. Similarly, the mole fraction is going to be the number of moles of the solute over the total number of moles. Another little beautiful moment of cancellation. The total number of moles ends up canceling out, and I get RT times the moles of solute over the total volume. Well, that's the same thing as molarity. So congratulations, this is the one time where molarity will honestly show up in thermodynamics. Don't get used to it. We won't see it again until kinetics. But again, this is a useful feature. We can actually determine the molarity of a system through a simple measure of the osmotic pressure. And it turns out that this is actually a fairly useful way to determine the molecular weight of an unknown compound using a technique called osmometry. So you can actually buy specially made osmometers, or you can try and set up the apparatus yourself. It gets a little bit tricky as you're gonna have to carefully measure pressures. But let's say I have an osmometer on hand. Well, we can essentially use it to determine the molecular weight of, say, I place 1 gram of hydrocarbon into 1 liter of water, and my osmometer gives me a pressure back of 0.885 bars required to keep the system at equilibrium. So using this information, I can quickly determine the molarity of the system, as it's just going to be the osmotic pressure, 0.885 bars, over RT. So it gets me back a molarity of 0.035. Now, what I can do is make use of the fact that I'm trying to determine the molecular weight, which is just the mass over the number of moles. Well, let's go ahead and rearrange this guy a little bit. Whereas I can have, say, express this as the mass over volume times the volume over the number of moles. Well, I have the mass and the volume volume over the number of moles is the same thing as 1 over the molarity. Now I have all three of these numbers. I can then simply input in my values, and we get back a molecular weight of 28 grams per mole. Now, since I told you this is a hydrocarbon, this is going to leave us very few options. And it turns out that this is actually going to correspond to a compound of ethene, which again, 2 carbons at 12 apiece, plus 4 hydrogens, 28 grams per mole. So again, it's a very useful metric of if you can determine the concentration of any colligative property, whether it's osmotic pressure or freezing point or boiling point, you can determine the molecular weight. And again, the two most common techniques, because they tend to be the most sensitive and the easiest to measure, are going to be osmometry and freezing point depression, which again, freezing point depression having a very similar technique, except for you go after mole fraction or molality instead of molarity. But general concept is the same. However, we do run into a problem, which is that we generated our osmotic pressure equation assuming that we had an ideal system. Well, it turns out that not everything is ideal. So one of the classic techniques we have to deal with non-ideality of, say, our solute, which is probably going to come from a certain degree of molecular forces that are going to actually be present as my solute is going to interact with the solvent. So I can deal with this the way I often deal with things. I run a virial expansion. When in doubt, expand it out. So what we can do is say that our osmotic pressure is going to be related to our base form, and then we're essentially going to expand about the concentration of the system. because I know at very low concentrations, everybody should behave ideally. It's not until I get to higher concentrations that I have to worry about the intermolecular forces in between my solute and my solvent. So this actually makes logical sense for how I would run an expansion. Now, the problem is that now I'm left with an unknown term, because I can measure osmotic pressure, and let's assume that I can determine uh, my molarity of my system. Well, in this case, what I can do is try and get at this B term. Well, in order to do this, I'm going to try and simplify the system by dividing both sides by the molarity of the system. And in this case, what we have is I'm going to plot the osmotic pressure over the molarity of the system, and this is going to give me a intercept of RT and a slope of BRT times, again, the molarity of the system. So I'll plot molarity versus osmotic pressure over molarity. And from this, I can essentially get the non-ideality of the system. However, remember, one of the major features that I want to try and determine using osmotic pressure is going to be the molecular weight. Well, in order to get to the molarity of the system, I need to know the molecular weight of the compound I'm dealing with. So one of the tricks that we can actually do is try and convert our molarity into mass concentration. And when I do this, well, I'll go ahead and do this on the left side, but I'm going to do this by essentially dividing by having the molecular weight up top. Well, I can divide the right side by molecular weight, and I get RT over the molecular weight plus BRT over molecular weight squared times concentration. All right, this may not exactly seem like a great technique, but what happens is if I plot the mass concentration versus the osmotic pressure over the mass concentration, and remember, I can easily determine the mass of the system and the volume of the system, so that isn't too bad. And if I do this, what we end up with is an intercept of RT over the molecular weight. Well, from this, I can determine the molecular weight of my unknown compound. And once I have the molecular weight, then I can use my intercept, which gives me BRT over mass molecular weight squared, to determine my second virial coefficient. So whether we're trying to just determine the second virial coefficient, because I need to use the osmotic pressure at high concentrations, we can use this first technique of plotting it out. But if I'm trying to still determine molecular weight, we can essentially use this modified form. So we can use very similar tricks to examine the solubility of a solid going into the liquid phase in a mixture. So this is actually going to make the assumption that under a soluble system, we have the chemical potential of the pure solid is going to be equal to the chemical potential of essentially my new liquid phase, which can be expressed as the chemical potential of the pure liquid plus essentially counting for the fact that we have a much lower mole fraction. Now, the major assumption here is going to be that that the system is going to behave relatively ideally. So essentially, we're going to have to assume similar intermolecular forces in between my dissolved species and the solvent, which is not often a great case, especially as the mole fraction gets fairly low. However, we can actually determine what mole fraction this will correspond to by essentially trying to isolate the mole fraction term. So we subtract the chemical potential of the liquid from both sides and then divide by RT. Now, when we do this, you may notice that we're going to have the solid minus the liquid. So this is going to be the same thing as a freezing reaction, which again can be represented by the negative of the free energy of fusion, and then again divided by RT. Then what I can do is essentially try and integrate both sides. So the integration of the right side should be fairly straightforward, as I'm going to be integrating from the pure species to essentially the mole fraction of my maximally or saturated solute system. Now the right side actually gets a little bit trickier. However, what we can do is make use of the fact that since I'm going to have to find the derivative of natural log of x, I'm going to have a very similar expression here as I did for the freezing point uh, or boiling point elevation, and such. And using that assumption, I can make a very similar approximation and use the Gibbs-Helmholtz approximation to give me the change in enthalpy of fusion over RT squared. And again, you'll notice that this is going to look very similar to my enthalpy, to my boiling point elevation, with essentially just slightly different constraints. So when I do this, what we're going to end up finding is that the mole fraction, the natural log of the mole fraction of my saturated solute is going to be equal to the enthalpy of fusion over R times essentially the difference of 1 over my freezing point, freezing point minus 1 over the temperature of which I'm going to be looking at. Now, again, this is going to be a fairly useful sort of way to kind of estimate solubility. And that, again, we're going to not surprisingly see that the solubility is going to have a tight temperature control. But we do run into the slight problem that we made the assumption that the system behaved ideally, which again, you may note that Raoult's law should have long since broken down by this point. So this isn't exactly the best technique. So what we're going to do next time is try and focus with a little bit more detail on how I can essentially take all of these ideal equations I built up and essentially apply them to a non-ideal scenario. In order to do this, we're going to have to talk a little bit about activity, which is more or less the solution form of fugacity. So until next time, take care.